Hello everyone, my name is Emma Griffiths and I'm a research associate on the ontology development team in the Shao Public Health Bioinformatics Lab at the University of British Columbia in Vancouver, Canada. Welcome to Solutions for Overcoming Cohort Data Integration Challenges Using Ontology, an Introduction. In this short video, we'll highlight some of the challenges of integrating datasets across cohorts, we'll discuss how ontologies are useful tools for harmonization, and we'll describe some of the benefits of using them. Metadata is information about data. Cohort metadata can include information about individuals participating in a study, about samples, about experiments, and much more. Metadata is essential for making sense of data and performing analyses. Combining or integrating data and metadata across cohorts is beneficial for many reasons. For example, it serves to increase sample size and add statistical support, and can broaden the scope of a study. However, while metadata collected between different studies and cohorts can overlap, not all the variables and data types are the same, nor are they encoded the same way. This often adds complexity and makes integrating or fitting datasets together rather difficult. One of the challenges of integrating metadata across cohorts arises when different groups use field names differently. In this example, we see field names taken from different labs sharing Canadian pathogen surveillance data. Here, we see that 4 labs have used different fields to mean the same thing. All of the fields in the top bracket are ways of describing the material from which the pathogen was isolated, or the isolation source, which I've annotated in red. Now, while a person can probably figure that out, a computer sees the different labels and doesn't recognize that they mean the same thing. In contrast, the 5th lab also used a field called source, seen in the lower bracket. But in this case, source is used to indicate the name of the lab that collected the data, which I've annotated in red. Here, the computer sees identical labels to the one above and can't recognize that they mean different things. Another challenge to integrating datasets is when the allowable values for a field differ. In the tobacco use example presented in the slide, Cohort A allows participants in the study to be classified as either smokers or non-smokers, whereas Cohort B classifies tobacco use with a scale or a range of values. Combining tobacco use data between these cohorts is not trivial. Another common challenge to harmonizing data across cohorts is when the same experimental variables between different studies have implicit assumptions, or in other words, when data types are named the same way, but the methods or criteria used to interpret the data are different. In this example, we see that 2 studies have both carried out allergy skin prick tests on their cohorts, and the criteria for determining the outcome of the test is determined by the size of the swelling after an allergen is applied. The cutoff value for determining a positive result is different for each cohort. Anything larger than 2 millimeters in swelling is considered a positive result for cohort A, whereas the swelling should be larger than 5 millimeters to be considered positive for cohort B. The experimental variable name, however, positive skin prick test result, is encoded in the same way in both studies. These methodological differences are not obvious to a person or a computer that just sees the variable name, but they have significant impacts on how the results from the different studies should be combined. Ontologies present many solutions to these challenges, as they're essentially a means for standardizing the meaning of terms, and a means to compare information at different levels of granularity. Ontologies are ways of structuring information. They contain controlled vocabulary arranged in a hierarchy with more general terms at the top and more specific terms at the tips, as in this excerpt from a hypothetical food ontology that you can see in the slide. Every term is clearly defined and the meanings of the terms are disambiguated through the use of unique identifiers. One of the key differences between data dictionaries and ontologies is that ontologies also contain logical relationships between terms. Now, these logical relationships can be very simple, such as the is-a relationship. So, for example, in the top right hand of your screen, you can see that a hen egg product is a type of poultry egg product. Or these logical relationships can be used to link information in more complex ways. So, for example, a chicken product is the input of a particular dietary plan, or ready-to-eat sliced chicken breast has a quality of light meat. This logic is built in by domain experts and provides greater querying power over data that's annotated using ontologies. So in this example, if you had a data set annotated with this food ontology, you could perform a query to determine all the participants in the study that ate foods that were part of a particular diet or had particular qualities like light meat. Ontologies can also incorporate synonyms, alternative spellings, and different languages, which enables you to keep using the terms that you're used to and doesn't force you to use anyone else's data dictionary. So, just to recap, ontologies contain controlled or standardized vocabulary arranged in a hierarchy, in which terms are carefully defined and are assigned unique IDs. Ontologies also incorporate synonyms to provide greater flexibility for both systems and users. And the logical relationships enable you to inference over data sets and ask more difficult questions. We'll discuss how you can start using ontologies in an upcoming video. So, how can ontologies help resolve some of the challenges that we discussed earlier? In the first case, data from different cohorts can be annotated with ontology terms that disambiguate the meaning of fields using standardized terms and definitions. Ontologies enable descriptors at different scales and levels of granularity, which can be compared using the hierarchy of the ontology. Ontologies can also help to make implicit assumptions in variables more explicit by annotating data with terms that can be differentiated using specific IDs. So in summary, the three major advantages of using ontologies are that they, 1, provide standardized terms, which means the datasets annotated with ontology terms require less manual data cleanup and are more understandable by humans and computers. And the data becomes more interoperable, so the datasets can fit together better and can be more effectively used by different systems. 2, they provide structured inputs and outputs, as opposed to free text or lab or study-specific encoding, which means that you can build more analytical tools based on the expected inputs and outputs, which can improve automation and transformations of data. 3, ontologies also help improve communication between labs and researchers because the meaning of their data is more clear, and the emphasis is placed on matching concepts and meaning rather than just text matching. Thank you for watching our introduction to ontologies. In our next video, we'll discuss ways to start annotating data with ontologies. For more information, please check out our websites genepio.org and foodon.org. To contact us, please send us a message at info@genepio.org. See you next time.